There is a thought experiment I find myself returning to, one that begins not with rockets or stars, but with a simple calculation done on the back of a napkin. You take the nearest star to our sun, a small red dwarf called Proxima Centauri, and you ask a straightforward question: how long would it take to get there? With our fastest spacecraft ever launched, the answer is roughly 70,000 years. 70,000 years. That number sits there, quiet and enormous, and it does not care how ambitious our plans are or how inspiring our visions of the future might be. Physics, as it turns out, has a way of being unmoved by human ambition. Now, I want to be precise about what I mean by the uncomfortable truth in that title, because I am not talking about whether humans will ever leave Earth orbit again or whether we might someday build a colony on Mars. Those are engineering challenges, difficult ones, but not fundamentally impossible. What I am talking about is something far more sweeping: the idea that humanity as a species will spread across the galaxy, seeding worlds with civilization, hopping from star to star the way Europeans once crossed oceans. That vision, the one that science fiction has handed us so generously, runs directly into a wall built not by lack of imagination, but by the laws of physics themselves. Let us start with the speed of light, because everything in this conversation leads back to it. Albert Einstein in 1905 showed that the universe has a cosmic speed limit, and that limit is approximately 300,000 kilometers per second. Nothing with mass, and that includes every atom in your body, every molecule of a spacecraft, every gram of fuel, can ever be accelerated to that speed, let alone past it. You can get close in principle, though the energy required to do so grows without bound. As you approach the speed of light, your effective mass increases, and the force you need to push yourself even a tiny fraction faster grows exponentially. The universe does not say slow down politely. It says the price for going faster is infinite, and it means it. So let us imagine that we build the most extraordinary rocket imaginable, one powered not by chemical combustion, not by ion thrusters, but by the most efficient energy source physics permits, the annihilation of matter and antimatter, converting mass entirely into thrust. Even with that ideal engine, accelerating a crude spacecraft to, say, 10% of the speed of light would require a staggering amount of antimatter fuel, far exceeding anything we could conceivably produce or carry. The mass ratio problem, the relationship between the fuel you need and the payload you are trying to move, is ruthless. It does not care about engineering cleverness. It is baked into the mathematics of momentum and energy. But suppose we solve it. Suppose through some future miracle of engineering, we get a ship to 10% of the speed of light. Proxima Centauri, at 4.2 light years away, would take 42 years to reach. That is one human lifetime, manageable perhaps for a dedicated crew. But Proxima Centauri is our closest neighbor, an exception rather than the rule. The galaxy is 100,000 light years across. Even at 10% of light speed, crossing it would take 1,000,000 years. And that is not a story of exploration. That is geological time. That is the duration of entire species rising and falling on this planet. Human civilization in its entirety is roughly 10,000 years old. 1,000,000 years is 100 of those civilizations, stacked end to end. Now here is where the physics becomes even more humbling, and where I think the deeper truth lives. There is a concept in general relativity called timedilation. Einstein showed that time does not tick at the same rate for everyone. A clock on a fast-moving spacecraft runs slower than a clock at rest. The closer you get to the speed of light, the more dramatic this effect becomes. At 99% of the speed of light, time for the traveling crew passes at roughly 1/7 the rate it passes back on Earth. This sounds like a solution, and some popular accounts treat it as one. The crew ages only a few years while centuries pass at home. But notice what this means. The people you left behind, your civilization, your culture, your accumulated knowledge and institutions, they age and change and die while you are in transit. You arrive at a distant star not as a representative of a living civilization, but as a relic of one that has long since transformed beyond recognition or collapsed entirely. The traveler and the sender are permanently severed by physics. There is no radio call home that arrives quickly enough to matter. Light itself is too slow to maintain meaningful connection across those distances. Let me make this concrete with an analogy. Imagine you could bottle a message and throw it into the ocean, and the bottle would take 1,000 years to reach the other shore. Any reply would take another 1,000 years to return. Could you maintain a civilization across that ocean? Could you coordinate, share knowledge, govern, adapt? Of course not. The ocean of space is not a metaphor for inconvenience. It is a literal information barrier enforced by the speed of light. No signal, no command, no piece of news can travel faster than light. A galactic civilization, if we imagine it honestly, would be a collection of isolated pockets of humanity, each evolving independently over millennia, cut off from one another more completely than any two cultures on Earth have ever been cut off from each other. That is not a civilization. That is speciation. It is the slow divergence of isolated populations into something unrecognizable. Some people at this point will invoke the possibility of wormholes. Those hypothetical tunnels through the fabric of space-time that general relativity technically permits under certain mathematical conditions. Einstein and Nathan Rosen first described these solutions in 1935, which is why physicists sometimes call them Einstein-Rosen bridges. And yes, the equations of general relativity do allow for geometries of space-time that connect two distant regions through a shortcut. The mathematics is real and legitimate. But here is what the mathematics also tells you. To keep a wormhole open, to prevent it from collapsing, would require a form of matter with negative energy density, something we call exotic matter. We have never observed exotic matter of the required kind. We have no evidence it exists in the forms needed. The Casimir effect hints at something like negative energy in quantum mechanics, but the tiny, constrained quantities involved are nowhere near sufficient to prop open a traversable wormhole large enough for a spacecraft. Physicists who study this seriously are not optimistic. The word they tend to use is probably impossible, which in science carries more weight than it might seem. It is not the same as we have not figured it out yet. It is closer to the structure of the laws themselves seems to forbid it. There is another popular escape route, suspended animation or some form of biological stasis that lets a crew sleep through the centuries. This is an engineering challenge rather than a physics impossibility, so I will be slightly more generous here. If humans could be frozen and revived without damage, you might put a crew to sleep for a 1,000-year journey. But notice that you have now created a different problem. Who maintains the ship? Who makes repairs when a micrometeorite punches through a hull panel in year 300? Who navigates when the automated systems fail, as systems inevitably do over centuries? The engineering reliability required for a 1,000-year unmaintained spacecraft journey is so far beyond our current capabilities that it functions, practically speaking, as an impossibility. We build things that last decades with heroic effort. The Voyager probes, our most enduring spacecraft, are now pushing 50 years and were not designed to last this long. A 1,000-year journey requires systems 100 times more durable, with zero possibility of a service call from Earth. And then there is the biological reality of the human body itself. We evolved on Earth. We evolved under one gravity, under a specific magnetic field that shields us from radiation, under a particular spectrum of light with a specific ecosystem of microbes and foods. Space is extraordinarily hostile to the biology we are. Prolonged weightlessness causes bone density loss, muscle atrophy, fluid shifts that damage vision, and immune system changes we do not yet fully understand. Cosmic radiation, the high-energy particles that stream through interstellar space unimpeded by any planetary magnetic field, is carcinogenic at the doses a multi-decade voyage would involve. We can mitigate these effects with medicine and engineering, but mitigation is not the same as solution. The human body is an exquisitely tuned instrument built for one specific environment, and that environment is this planet. I want to pause here and address the response I know is forming. What about genetic engineering? What about cybernetic enhancement? What about uploading human consciousness into a digital substrate that could survive radiation and centuries of travel? These are fascinating ideas, and I do not dismiss them. But notice what has happened when we pursue them. We have stopped talking about humans going to the stars, and we have started talking about something else, something post-human, something that has been so radically altered from the biological creature that walked out of the savannas of Africa that calling it humanity is a philosophical stretch at best. The question becomes whether the thing that reaches the stars would bear any meaningful continuity with the civilization that sent it. And that is a profound question about identity and continuity that goes well beyond the physics. Here is perhaps the deepest cut of all, and it comes from thermodynamics, from the irreducible arrow of time and the inevitable decay of complex systems. Stars are not eternal. Our sun will exhaust its hydrogen fuel in roughly 5 billion years and expand into a red giant. But long before that, in about 1 billion years, its increasing luminosity will boil Earth's oceans. The timescales for interstellar travel are not just long relative to human lifespans, they are long relative to the window of habitability that Earth itself provides. If humanity is going to survive as a multi-stellar civilization, it needs to do so on timescales that dwarf the entire history of complex life on this planet. Physics is not just setting the speed limit, it is setting the clock. Now, I want to be honest about where this leaves us, because the truth is not quite as simple as saying it is impossible and sitting down. Physics sets hard limits, but within those limits, there is still an enormous space of possibility. Mars is, by cosmic standards, right next door. The challenges of getting humans to Mars and keeping them alive there are extraordinary, but they are not physics impossibilities. A permanently crewed outpost on Mars, a second foothold for life in this solar system that is within the reach of physics and perhaps within the reach of engineering in the coming century. The moons of Jupiter and Saturn offer environments that are strange and fascinating, and robotic probes can explore them in ways that extend human knowledge enormously. The outer solar system is vast, and we have barely begun to map it. But a solar system civilization is very different from a galactic one. And here is the subtle intellectual honesty that I think we owe ourselves. For decades, popular culture and a great deal of scientific optimism have proceeded on the assumption that the galaxy is our destiny, that the stars are merely a technical problem to be solved, that given enough time and ingenuity, humanity will do what it has always done and expand without limit. Physics suggests this picture is, at its foundations, wrong. Not because we lack ingenuity, but because the universe was not built to accommodate our intuitions about expansion. The speed of light is not a suggestion. The inverse square law of energy required to accelerate mass is not a rough estimate. These are the ground floor of reality, the level below which there is nothing to excavate. What the physics really tells us is that the universe is extraordinary at scales that do not require travel. The light arriving at your eye right now from a distant galaxy left that galaxy billions of years ago when Earth did not exist. That light has been traveling through expanding space, carrying information about a cosmos we can study and marvel at and describe mathematically without moving a single meter. The observable universe is 93 billion light years across, and every cubic meter of it is accessible to our instruments, our equations, and our imaginations. We are not barred from the cosmos. We are simply barred from walking across it. And perhaps there is something worth sitting with in that. The universe is structured in such a way that information, light, mathematics, understanding, these things flow across the cosmos at the maximum speed physics permits. But physical matter, physical bodies, physical civilizations, they are rooted, they are local. They are bound to the particular corner of space where the conditions that built them happen to exist. That is not a failure. That is the nature of complex physical systems embedded in the fabric of space-time. It is what it means to be made of matter in a universe governed by the laws we have spent centuries uncovering. The uncomfortable truth of that title is not that we have failed or that we should stop reaching. It is that the reaching itself, the telescopes trained on distant worlds, the equations describing space-time curvature, the particle accelerators probing the smallest scales of reality, that is the form our cosmic participation takes. Not boots on alien soil, but minds comprehending alien suns. The galaxy does not open its doors to our bodies, but it has never, not once, blocked our curiosity.